Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic, triple integrals. Okay, so we talked a lot about double integrals last time, double integrals in rectangular coordinates, double integrals in polar coordinates, area, things like that. Triple integrals are just looking at changes in volume, essentially, as opposed to changes in area. All right, so we have a function of three variables. So we start with a function f of x, y, z, and it's defined on a closed, bounded region in space. And we'll start with a very simple case where the region in space is just a rectangular region, like a box. So e.g., the region could be the box where x is between a and b, and y is between c and d, and z is between e and f, right? So we have this rectangular box. Okay. Try to draw this thing over here. So let's see here. And something like that, and then that'll connect up there, and that'll sit like that, and there, and there. So there's a pretty good box. And this thing sits in the xy plane, so maybe there's the y-axis, and maybe there's the x-axis, and maybe there's the z-axis, right? So this thing is sitting in the xy plane somewhere. And let's see what I want to label here. So the x limits are, so maybe there's a, and there's b, and there's the y limits, and the z limits. There's e. Okay, so there's probably the simplest region under consideration here, because we started off with rectangular regions in the plane when we talked about two integrals. Now we have rectangular regions in three space for triple integrals. Okay? And the idea is we can partition the box into sub-boxes and look at delta V of each sub-box, right? So we looked at delta A for each sub-rectangle in the plane. Now we have delta V of each sub-box, right? And delta V is the volume of each sub-box, and it's delta X, delta Y, delta Z, right? So a change in X times a change in Y times a change in Z. Just like the sub-rectangles in the plane were delta X, delta Y, okay? And I'm going to omit most of the details here, because we already went through this for the two-integral case. It's the same idea. So you form a triple Riemann sum, and then you pass to the limit and pass to the limit, right? And you get the following thing. So the triple integral of the function f of x, y, z on the box AB cross CD cross EF. And this just means x is between A and B, y between C and D, z between E and F, is the following thing. So triple integral, we'll call the region B, it's a box, of f of x, y, z dv. And there was a theorem for double integrals that we used that showed us we could evaluate these as iterated integrals. Well, the same theorem applies here. This is just integral e to f, c to d, a to b. So these are just iterated integrals. There's z, there's y, there's x, f of x, y, z. And in this case, we're integrating with respect to x first, respect to y second, respect to z third. So this is dx, dy, dz. And this is Fubini's theorem, which is the same theorem we had for double integrals, only this is the triple integral case. So Fubini's theorem for triple integrals tells us that we can evaluate these integrals as a series of 3 iterated integrals. Okay, so, and again, just like we had different orders of integration for double integrals, right? You could have gone with respect to y first, with respect to x first. Here, there are actually 6 different orders of integration for triple integrals, because you could go like this, dx, dy, dz. You could go dx, dz, dy, for example. You could go dy, dz, dx. So there are 6 different ways to order these up. And again, it may be that some ways of doing it are easier to do than others computationally. Okay, let's look at an easy one. So get rid of the box. We know Fubini's theorem and the definition of triple integrals, so we're ready to go with this. And if we're just given one over a nice box region, so let's evaluate triple integral over b of x, y, z squared dv. And let's do it over the box region where x is bounded between 0 and 1, y is between -1 and 2, and z is between 0 and 3. So it's a nice rectangular box region. Okay. All right, so triple integral over b we can write as a series of 3 iterated integrals. And in this case, I don't see any particular reason to go in any other order than we did in the first place. So we'll go ahead and do dx, dy, dz. So we'll integrate from 0 to 3, and then where am I? -1 to 2, and the x limits are 0 to 1. Function is x, y, z squared, and we're going dx, dy, dz, right? Okay. So we want to integrate with respect to x first. So let's see here. We've got 0 to 3. We've got -1 to 2. This is a constant in terms of x. So what have you got? 1/2 yz squared x squared, right? Do you want, well, I should put my limits up here too. So from limits of integration are from 0 to 1 and dy dz. Okay. And so what do you get there? So let's see, you got 0 to 3, you got -1 to 2. So you plug in 1 for x here, you get 1/2 yz squared. This part zeroes out, so your new function is 1/2 yz squared dy dz. Right? Okay. So let's see. Now this is the integral from 0 to 3. So the function is what? 1/4 z squared y squared, right? Yeah. Does that look right? Yeah. Mm-hmm. And that's from -1 to 2, and you got dz there. Is that what I have here? Yeah. Yeah. Good. Okay. And let's see. So you plug in for y squared. The 1/4 and the 4 makes a 1. This is just a z squared. And the -1 squared is a 1. So you have z squared minus 1/4 z squared. So your new function is 3/4 z squared dz, right, from 0 to 3. And that gives us, excuse me, 1/4 z cubed. Is that right? Yeah. Mm-hmm. And that's evaluated from 0 to 3. So 3 cubed is 27. So this is 27/4. Is that what I got? Yeah, it is. Good. Okay. So there you go. So not a whole lot to this. you could have certainly gone in any other order that you wanted to go in, but there's no reason not to go in this order. There's nothing complicated about this, but any of the other 5 orders would have also worked as well, gives you the same answer. Okay, so they would have all given you 27/4 at the end of this. Okay, so what is more useful to us than just doing random triple integrals is this idea of volume, right? Just like double integrals could give us a way of computing areas in the plane, triple integrals give us a way of computing volume in 3 space, right? So just like the area of a closed bounded region in the plane was, we did the double integral of the region R, because I'm using D here, aren't I? Well, we'll use R, why not? dA, right? So we just integrated the function 1 over the region in the plane. The volume of a closed bounded solid in space is area B dV, right? So we're just integrating the function 1 over the region B. And I'm calling B stood for a box in our previous example, but we're going to see that, B need not be a rectangular box-like structure. It could be any solid that we want to deal with. Just like we had more general regions in the plane, we'll also have more general solids in space. Okay, so an example of that would be something like this. So there's the formula we need. It's analogous to the area formula, only it's in 3 dimensions. Okay. So let's find the volume of the tetrahedron bounded by the following planes: x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay. Okay, so what we want here is we need limits of integration for x, y, and z. So we need 2 drawings rather than just 1. We need 1 drawing of the surface in space, and we need 1 drawing of its projection onto a plane. And in our case, it'll be the xy plane, but, well, any plane will really do. So it could be the xz plane or the yz plane just as well sometimes. So we do need 2 drawings here. Need 2 drawings, right? We need 1 showing the z limits of integration. That is to say, a drawing of the surface in space. All right, we need 1 showing the surface in space in the z limits. And the other showing x and y limits of integration. And that's a drawing of the projection of the surface onto the xy plane. So we'll have 1 3D drawing showing the z limits and bounding surfaces. We'll have 1 2D drawing showing the x and y limits integration and the bounding curves. Okay, so let's get rid of all this. We have our problem. We know what we're doing. Let's draw our pictures. This is usually the hardest part of any kind of multiple integration problem, is finding these limits. Once you've done that, it's kind of a standard process of integrating as long as your functions are decent. So we need a picture of the plane z equals 1 minus x, that's a y, minus y, right? Because our plane to start with was what? X plus y plus z equals 1. Right? So we need this plane. So this is a plane that goes through the following 3 points. It goes through what, 0, 0, 1, and it goes through, so if y and z are 0, then we have x equals 1, so we have 1, 0, 0. And if x and z are 0, then y is also equal to 1, right? So 0, 1, 0, right? So, okay. So it passes those 3 points, and we can draw that up here. So let me draw the axes up first, and then we'll kind of erase wherever we see fit. So there's the points we need to pass through. All right, so we need this thing to look sort of rectangular. Oh, I'm sorry, triangular, not rectangular, triangular, right? And let's kind of, so this is all the axes in here are all behind the plane. So these are all behind the plane. Like that, right? And there's the plane, so this is going to work to shade it in here, but, well, okay. Right. So there's the plane that we care about. And the surface, this surface here, is also bounded by the positive axes. So, I mean, this plane goes on forever. This plane goes on forever. We know that, but we only care about its bounding between the positive axes, so it's like this tetrahedral region in here. Imagine this is coming out of the board at you, and behind it sits this solid, right? That is tetrahedral. So what we want is we want an upper and lower bounding surface. Well, the lowest z value this thing goes to is z equals 0, right? In other words, in the xy plane, z is 0. That's the bottom of the tetrahedron here, right? That's the bottom. So that's one bounding surface. And at every point above that, the z value is this 1 minus x minus y. So our upper bound for our surfaces is going to be that plane there, right? So it's going to be z equals 1 minus x minus y. And our lower bound, the lower z values are always 0. So it's going to be z equals 0, right? So the bottom line is that z is stuck between 0 and 1 minus x minus y, right? Okay. There's our z limits. All right. So that's the z limits. Everything's okay there. Okay. Let's do the x and y limits. So to do that, we need, let me leave just that part, we need to look at the projection of this surface onto the xy plane. So let's change colors maybe to get a little variety in ourselves. So how does this thing look? Well, so let me start here. We have x plus y plus z equals 1. That's the top bounding surface, right? Okay. Well, when z is 0, i.e. in the xy plane, this thing is just x plus y equals 1 or y equals 1 minus x, which is a line, right? And it's also bounded by the coordinate axes. So it's bounded by x equals 0 and y equals 0. So it's in the first quadrant, and it's the line y equals 1 minus x. In particular, it's that region right there, right? This is the line 1 minus x restricted to the first quadrant. And this is 1, 0, and this is 0, 1, right? Okay. So that's what our surface looks like in the xy plane, right? We're moving from top to bottom. Well, I need a different color. That's not going to show up. So we're moving from top to bottom for the y limits, right? There's the bottom y curve. There's the top y curve, right? So what is y bounded between? Well, y is between y equals 0, the x-axis, and the curve 1 minus x, right? Mm-hmm. And the x is bounded between, well, 0 and 1, right? So x is bounded between 0 and 1, right? Okay, so we have our limits, all right? Let's do our integral. So there's a picture in the xy plane. Remember the z limits. We have x and y limits. We're ready to go here. So, what do I want to go to? Let's go to black. So the volume is just triple integral b dv, which we'll now write in terms of 3 iterated integrals, starting with dz, then going to dy, then to dx, right? So this is the integral. There's the x limits. There's the y limits. What were the z limits again? 0 and 1 minus x minus y, right? dz, dy, dx, right? Now we're doing dz first because we have it in terms of x and y, dy second in terms of x, dx third. It's just constants, right? Okay. So let's start this here. So 0 to 1, 0 to 1 minus x of z ranging from 0 to 1 minus x minus y, dy dx. Okay. That's the integral from 0 to 1, 0 to 1 minus x of 1/2 z squared. Oops. Wait, no, I'm not doing this right now. It's the integral of 1 minus x minus y. That's better. dy dx. Dy dx, yeah, okay. Okay, so now integral from 0 to 1. What's the integral here in terms of y? Well, look at this. I mean, the inside integral is going to be minus 1, and this whole thing would be times 1/2 and then squared, right? Because this is just like a expression that was, the whole thing was squared times the integral of the inside, like, you know, reverse chain rule. And so what we have here is what? Negative 1/2 times 1 minus x minus y squared, evaluated from 0 to 1 minus x dx. Again, this is reverse chain rule, so you're thinking about this multiplying out to a -1, since the integral of negative y, or derivative of negative y was -1, where the negative came from out front, right? Okay. So let's see, plug in 1 minus x here, you get 0. That whole part zeroes out. Then you plug in 0. We can actually kick the constant out front. That doesn't change anything, right? That can just go out front and get rid of it. Integral, so that goes out front. And this is left with just a 1 minus x squared, like that, dx, all right? Okay. Let me come over here, actually, and keep going rather than going down. Okay. So again, we need the integral of the inside piece is just a -1. Integral of the outside piece is looking like a 1/3 1 minus x cubed. All right. So we have this -1/2, and then you're integrating. Let's see here. So it's going to be -1/3 1 minus x cubed, integrated from 0 to 1. Right? Does all look good to me here so far? Yeah, it does. It does. Let's see here. Everything look all right? Should there have been a negative out here? Should there have been a negative? Let's look at this again here in a minute. So that's a -1 minus x, and oh yeah, it should be. I'm sorry. Yeah. So okay. So back up here 1 second. So when I did this subtraction here, this gave me a 0. Then I had minus a 1 minus x minus 0 squared. So there should be a negative here. That's where it came from. Okay, because I did the minus this piece. So it should be a negative there. So this should actually be positive. That'll make it right. Yeah, there we go. Okay, that's positive. Okay. Let's see. Plug in. You get what? -1/6 times 1 minus 0. 1 minus, so that's 0 cubed minus 1. So -1/6 times -1 gives you a 1/6. Yeah, that looks good. Is that what I have here? Yeah, it is good. Okay. So there is your volume. And again, the hardest part of this was finding these limits here. once you got past that, it wasn't too terribly bad. If you don't like doing it this way, you could have always expanded out here and done polynomial integration, but this might be a little faster doing it by chain rule calculation. But either way it works, you should get 1/6. Note also, I mean, you could have certainly done other things, like you could have solved for y to start with and done it that way, but there's no reason to here. But, I mean, there are other orders of integration that would also work here to give you the same value, but this one may be the easiest computationally to handle. Okay, so let's try a little harder one. So that wasn't too bad with the tetrahedron. Let's see, so there's the answer, there's all the calculations, we have that. And let's try doing one where we're going to need to do a change of order of integration, otherwise it's going to be too hard. So let's try this one. So let's start by at least setting up the integral to find the volume of the region bounded by the paraboloid y equals x squared plus z squared and the plane y equals 4. Okay, so I'm going to start by doing this the same way we just did it, using z first, then y, then x. But it turned out actually that may not be the best way to do things. Let's see how things look. So again, you want two drawings. And you want one of the surface in space and one of the projection in the xy plane, right? Two of those drawings. Okay, so the paraboloid x squared plus z squared is symmetric across the y-axis. So what we have is something that looks sort of like, let's see here. How's that? I've seen worse, I guess. Okay, so there's a paraboloid. It's decent, I guess, and it has those elliptic cross sections, right? Circular cross sections, actually these are circular cross sections, but, and then it's, let's see here, so it's between, so there's the y-axis, right, and the z-axis is coming out like that, and the x-axis is going down like that, right? So there's the paraboloid centered around the y-axis, right? And this point right here, right, this is the point 0, 4, 0, right? This is a circle of, oh no, so never mind, that's not a circle. So this is the plane y equals 4. This is where it cuts off the paraboloid, right? So the plane cuts it through right here. That's where it ends, just this paraboloid here, okay? So this is the region y equals x squared plus z squared bounded by y equals 4. And then over here, we'll draw the corresponding projection. Well, in this case, in the xy plane, right, so when z is 0, this thing makes the parabola y equals x squared, and y equals 4 becomes not a plane, but a horizontal line, right? So up here's the line y equals 4. There's y equals 4. And the parabola y equals x squared, it looks like that. So there's the point -2, 4. There's the point 2, 4, like that, right? And then the shaded region inside the parabola is the projection of the paraboloid onto the xy plane. Okay? So again, when z is 0, this is y equals x squared, and y equals 4 is a horizontal line. Okay, so that's a pretty nice projection, honestly. Okay, so we need z limits. Well, again, we need top and bottom boundary surfaces here. So we know that this thing is not a function of z as it's written, right? Because it fails that vertical line test or the vertical plane test in 3-space, really. So we need to go ahead and take this thing and break it down into 2 separate functions, one defining the top part of the surface, one defining the bottom part of the surface, right? So where am I here? Z limits of integration, so they run from top boundary surface to bottom boundary surface. Okay, so they run from the top boundary surface to the bottom boundary surface. And so where am I now? So I got z squared equals x squared minus y, right? No, wait, y minus x squared, sorry. Y minus x squared, okay? And so z is either equal to square root of y minus x squared, or it's equal to the negative square root of y minus x squared, like that, right? And so this is clearly always positive, so it's the top boundary surface, right? It corresponds to this top piece, so this is z equals square root y minus x squared. There's the top piece of the paraboloid. And the bottom piece is always negative, right? So the y-axis cuts through this thing at the center, bounds top and bottom of the z-axis. So this is positive z, that's negative z. So this is going to be the bottom boundary surface. Bottom boundary surface. Okay, so this down here, that's z equals negative y minus x squared. Like that, right? So there's your z limits. Let's see, I'm running out of board space here, but I don't want to erase anything. Let's get rid of maybe this verbiage up here. So let's leave our pictures. All right. So here, we need x and y limits. Well, again, y is very clearly between a top curve and a bottom curve. The top curve is the horizontal line. The bottom curve is the parabola. So y limits run from not a top boundary surface, but a top boundary curve to a bottom boundary curve. Right? Again, the top boundary curve is y equals 4. The bottom boundary curve is always y equals x squared. And the x limits of integration are just constants. They run from -2 to +2. And then x limits are from -2 to +2, like that. Okay? So there's the bounding surfaces for z, the bounding curves for y, and the limits for x. So we're finally ready to begin actually setting our integral up. All right? So let's get rid of this. We'll leave all of our limits. I've got them all, yeah. So the region of B dv is -2 to 2, x squared to 4, and negative square root y minus x squared to positive square root y minus x squared dz dy dx. So that's the integral that would give us this volume. Now, the problem is, if we try to go through and actually compute this, it becomes very hard. Once we have these expressions plugged in for z, then getting dy is very challenging, right? Because this is no longer an elementary function of y. So this is too hard to evaluate. Okay. But all is not lost. We can always reverse the orders of integration in some way, maybe draw some new pictures, and try to work with things that way. That's our plan. So we're going to consider alternate order of integration. And in fact, it might have been the case even that the way the problem was written almost implied this order first because of the following. So if you recall, let me make some room here first because we no longer need this picture, and we're changing all of our limits, so the old limits no longer apply. All right, so let's consider the surface as a function of y. And what I mean by this almost naturally lends itself to this would be the fact that originally our problem was written in terms entirely of y, right? It was bounded by that surface and that plane, okay? And so if this is the case, well, I mean, you can almost see it still in the lines over here, but our paraboloid, remember, it looks something like that, right? Think about it in terms of the y-axis, right? This is the farthest out that the y-axis goes, up to y equals 4. And this is, and as it goes backwards, it extends further and further back towards 0 along these cross sections here, these circular cross sections, right? So now this is our quote-unquote top boundary surface. Top in the sense that it is the most far out on the positive z-axis, and this is our bottom boundary surface. It is less far out on the z-axis. It's always smaller than this surface over here, right? So this is our bottom boundary surface. So I'm kind of using top and bottom here not to mean what they mean in terms of height, but in terms of limits of the integral, okay? So this means that our y is stuck between those two things. So if we do the integration with respect to y first, then we have an expression in terms of x and z, right? Okay. So now there's no need to look at the xy plane anymore because we already have y done. Look at the projection in the xz plane, right? Okay. So any of the planes will do, it doesn't matter. Whichever variable defines your surface, look at the projection in the plane of the other two variables, okay? And like I said before, in the xz plane, this thing forms circular cross sections, right? In particular, right? Let's see here. So when y equals 4 is the biggest cross section that there is, right? This is the biggest circular cross section that gets smaller from here, progressively smaller until we're down to a point, right? So when y equals 4, what we have is 4 equals x squared plus z squared. That's a circle of radius 2. And from there, so from this circle, the circles get smaller and smaller and smaller, but they're all the same center, right? So if I put up here the biggest circle, right? So that's 0, 2. Notice this is the xz plane, not the xy plane. So this is x is 0, z is 2, and this is 2, 0, where x is 2 and z is 0. So this is xz plane, right? Then everything inside of this circle is also part of the region of the integration, because they're all getting smaller and smaller. So our region is then the inside of this disk, right? Yeah, so it's the disk, x squared plus z squared is less than or equal to 4, right? Okay, and therefore, if we can define this in terms of z, well, again, z has a top surface, the top half of this circle. Z has a bottom surface, the bottom half of this circle, right? So the top curve for z, well, is just z equals square root 4 minus x squared, right? That's the top half of this thing coming from solving this for z, right? We'll get two answers. We'll get top half and bottom half because it's not a function. And the bottom curve for z is z equals negative square root 4 minus x squared, right? So that's the bottom half of this circle in here, okay? So there's your z limits, and your x limits come from just the x-axis, which ranges from -2 to 2. -2 less than or equal to x less than or equal to 2. So we have y limits, we have z limits in terms of x. So y is in terms of x and z. Z is in terms just of x, and x is in terms just of constants. Okay? So let's see if this is any easier. Hopefully it will be. If not, we may be kind of out of luck here. So let's try this thing again. Triple integral b dv. X limits first, z limits second, y limits third. So y goes from x squared plus z squared to 4. And then we're integrating with respect to y first, z second, x third. And this will give us the exact same volume that our previous integral would have given us if we'd evaluated it. Okay? Okay, so let's see how this works. So we got -2 to 2, negative root 4 minus x squared, 4 minus x squared root. Then we have y in terms of x squared plus z squared to 4 dc dx. Okay. So what happens there? Integral -2 to 2, integral blah, blah, blah of the roots. All right. So we wind up with, what, 4 minus x squared minus z squared dz dx, right? Okay, now things are probably going to get pretty ugly here because we see we have square roots and things like that, but we have a savior, right? Polar coordinates. This is a circular region in the xz plane, and that's exactly the time when we use polar coordinates to make life easy on us in a circular region in the plane, okay? So let me, what do I want to erase? Just the top part of this for the time being? Maybe. Yes, I do, okay. So the plan is we can convert to polar coordinates in the xz plane, right? And remember, the conversion factors were always x equals r cosine theta. And remember, this is the same thing. I mean, any angle I draw down here, this is just like x and y, right? So any angle I draw, theta, right? X will be the length times the cosine. Z will be the length times the sine, right? So now we have, rather than y equals r sine theta, we have z equals r sine theta. And we have r squared equals x squared plus z squared. So there's nothing to be uncomfortable about here. We're just in the xz plane, not the xy plane. Okay? Well, how does this help us? Well, right away, 4 minus x squared minus z squared becomes 4 minus r squared, right? Because there's r squared. What else helps us? Our limits are easier, so the r limits, well, r is just the radius, so the radius ranges from a point 0 out to a radius of 2, so our r limits just become constants, all right? And our theta limits, well, this is a circle, so it ranges from 0 to 2 pi, right? So we have a nice, easy expression involving r limits, theta limits. So I can probably leave that, I guess. We're going to convert over, right? And also, it's worth noting, too, what do I want to say here? No, that's okay. No, it's not worth noting anything. So we're going to go from limits of x, limits of z, and a function of z and x to limits of theta, limits of r, and a function of r and theta, dr d theta, right? So limits of theta are 0 to 2 pi. limits of r 0 to 2, our function's now 4 minus r squared. The one thing to remember, though, is that when we integrate with respect to polar coordinates, it's always f of r theta dr d theta and an extra factor of r in the integrand, right? So this has got to be r dr d theta. So don't forget the extra r. Don't forget extra r. Okay? Forget that guy. But now, this is pretty easy to deal with. So let me come, so everything's okay over here. We have our limits. We're all solid there. Let me come over here, finish working this out. And we see this is much easier than we would have had before, right? Less cumbersome. So 0 to 2 pi, and let's see here, the integral from 0 to 2 of 4r minus r cubed dr d theta, all right, okay, and let's see, that's the limits from 0 to 2 pi of, 2r squared minus 1/4 r cubed from 0 to 2 d theta, okay, and let's see here, so you plug some garbage in, what in the world do you get? So 0 to 2 pi. You get, so this is r squared is 4, so that's 8. That's 16, so minus 16 fourths, which is 4. So that's a 4 there. Is that what I have here? Yes, it is. Good. 4 d theta. And that, of course, is just 4 theta from 0 to 2 pi. And so what do you get out of all this? 8 pi is your volume. And so in this case, we were able to do it this way because the limits of integration were easier to deal with. We had a circular region. We could do polar coordinates and avoid having nasty stuff with square roots. Okay, so that concludes the section on triple integrals.